Have you ever looked at something ancient, like a sarcophagus in a museum, and just wondered, how do they know how old that is? Well, it's not a guess. It's actually science, and it comes down to this incredible little atomic clock that's built right into the fabric of life itself.
Yeah, so let's just jump right into that question. How in the world do you put a date on something that's, say, 10,000 years old? That's way before any written history, long before calendars as we know them. The secret, believe it or not, isn't buried in some ancient library. It's hiding inside the atoms of the thing itself.
Okay, so here's how we're going to break this all down. First, we'll look at carbon's radioactive clock itself. Then, we'll talk about how that clock actually gets started. After that, we'll figure out how to read the time, why it sometimes needs a little tweaking, and for a fun finale, we'll see what happens when we try to use this method in the deep ocean.
All right, first up, the clock itself. The secret to this whole thing starts with carbon. It's the building block for all life on our planet. But here's the thing, not all carbon atoms are the same. So, in nature, carbon comes in three main varieties, or isotopes. You've got carbon-12, which makes up almost all of it. Then there's a little bit of carbon-13. These two are stable, they just hang around. But then there's carbon-14. This is the one we care about. And when we say rare, we mean it. For every billion carbon atoms out there, only one is carbon-14. That's just mind-bogglingly rare.
And this chart just puts that into perspective, right? Look at that tiny, tiny sliver for carbon-14. That's all we're working with. But here's the beautiful part. Its rarity and the fact that it's radioactive, that's its superpower. See, because it's unstable, it decays over time. And crucially, it decays at a perfectly steady, predictable rate. And that is what makes it a clock.
And the way we measure that steady decay is with a concept called half-life. It's exactly what it sounds like. It's the time it takes for exactly half of a pile of a radioactive isotope to decay and disappear. It's this incredibly reliable, constant rhythm, like the universe's most patient metronome, just ticking away.
And for carbon-14, that magic number is 5,730 years. That's its half-life. So let's put this together. If you find an ancient bone and it has exactly half the carbon-14 it should have, boom, you know it's 5,730 years old. If it only has a quarter of its original carbon-14 left, well, that's two half-lives, so you double it, 11,460 years old. It's just beautifully simple and incredibly powerful.
Okay, so we have this amazing atomic clock. But that begs a pretty big question, right? How does this stuff even get inside a plant or an animal in the first place? And maybe more importantly, when exactly does the clock start ticking?
Well, it's all part of this fantastic natural cycle. It starts way up in the atmosphere, where cosmic rays from space are constantly zapping atoms and creating new carbon-14. This carbon-14 then mixes with oxygen to become carbon dioxide, which, plants breathe in. Then animals eat the plants, or other animals eat those animals, and it works its way up the food chain. So as long as you're alive and breathing and eating, you're constantly refreshing your supply of carbon-14. But the moment an organism dies, that's it. The intake stops. The connection is cut. And that is the precise moment the radioactive clock starts its long, slow countdown.
Okay, we've got the clock, and we know when it starts. So what's next? Well, the next huge challenge is figuring out how to actually read the time, especially when you're dealing with such a tiny, tiny amount of these C14 atoms.
The guy who first figured this out, a chemist named Willard Libby, won a Nobel Prize for it back in 1960. His original method was, it was brilliant but clunky. He basically had to wait and listen for the individual clicks of atoms decaying. But then, in the late 70s, everything changed with a technology called accelerator mass spectrometry, or AMS. Forget listening for clicks. AMS is like a particle supercollider for archaeology. It takes a sample, revs the atoms up to incredible speeds, and then uses giant magnets to sort them by weight. It allows us to literally count the individual carbon-14 atoms one by one.
And this right here shows you just how big of a deal that was. With the old methods, you needed a big sample, sometimes hundreds of grams. You might have had to destroy a huge piece of a priceless artifact just to date it. But with AMS, you need less than a milligram. We're talking about a sample the size of a grain of sugar. It was an absolute game changer. Suddenly, we could date things we never dreamed of dating before, like a single seed or a tiny thread from an ancient cloth. It completely opened up the past.
So we can count the atoms, we do the math, and we get a date. Sounds easy, right? Well, here's where it gets a little complicated. It turns out that a radiocarbon year isn't exactly the same as a calendar year. The atomic clock is amazing, but it's not perfect. It runs a little weird, so it needs to be corrected or calibrated.
So why the discrepancy? Well, it turns out the assumption that C14 levels in the atmosphere have always been the same is wrong. For one, the sun's activity changes, which affects how much C14 gets created. But the biggest disruptor? Us. Since the Industrial Revolution, we've been pumping huge amounts of old carbon into the air from burning fossil fuels. This carbon has zero C14 in it, so it dilutes the whole system. It's like we've been pouring a bunch of flat soda into a fizzy drink. It just weakens the concentration of the good stuff.
And scientists first cottoned on to this when they were testing artifacts from places like Egypt, where they already had a pretty good idea of the age from historical records. The radiocarbon dates just weren't lining up. As this quote explains, the radiocarbon ages were coming back too young. The atomic clock and the history books were telling two different stories, and they had to figure out how to get them in sync.
And the solution they came up with is just brilliant. And it came from trees. Think about it. Every year, a tree grows a new ring. So a tree with 500 rings is exactly 500 years old. It's nature's perfect calendar. So scientists could take a sliver from a very old tree, count back the rings to a specific year, say the year 1250, and then measure the carbon-14 in that specific ring. By doing this over and over, they created a master correction key, a way to translate radiocarbon years into actual calendar years.
And this wasn't some weekend project. This has been a massive, decades-long effort by scientists around the world. They've used long-lived trees like German and Irish oak, piecing together these tree ring records to build a continuous calibration curve that now goes back over 12,500 years. It's just a monumental piece of scientific detective work.
All right, so we've sorted out dating things on land. But what happens when we take our atomic clock and dive into the ocean? Well, as you might guess, things get complicated.
The biggest problem is something called the reservoir effect. You have to remember the deep ocean is a massive reservoir of very, very old water. It's been out of contact with the atmosphere for hundreds, even thousands of years. So the carbon-14 in that water has had a lot of time to decay. When that deep, old water comes up to the surface, it mixes in, and any fish or clam living there ends up incorporating that old carbon. It basically means they are born with an age that's already a few hundred years old right from the start.
And we're not talking a small difference here. On average, the surface of the ocean already has a radiocarbon age of about 400 years. So if you date a fish that just died today, it'll look like it's from the 1600s. Scientists have to carefully subtract this local reservoir age to get the real calendar date.
But here's a crazy story. There was a very dark period in our history that actually gave scientists an incredible gift for studying the oceans. During the atmospheric nuclear bomb tests of the 50s and 60s, we humans nearly doubled the amount of carbon-14 in the air. A terrifying prospect, but it created this massive artificial spike of C14, what scientists call bomb radiocarbon. This spike acted like a giant dye packet dropped into the global system. Oceanographers could track this bomb pulse as it was slowly absorbed by the oceans, and it taught them an incredible amount about how ocean currents work and how quickly they take up CO2 from the atmosphere. A very strange silver lining from a very dark cloud.
So when you think about it, from completely changing our understanding of human history to giving us this unexpected window into the inner workings of our oceans, radiocarbon dating has been just revolutionary. It's an amazing story of human curiosity, of how we figured out how to turn the steady decay of a single rare type of atom into a clock that can read the past. It makes you wonder, what other secrets are just waiting for us to find the right key to unlock them?